Hello everyone, I'm Shichao. Today I will present our work, BodyCompass, Monitoring Sleep Posture with Wireless Signals. This is a joint work with my colleagues Yuzhe, Hao, Rahul, and Dina from MIT. As you may or may not know, many people die in their sleep, and many of those deaths are linked to sleep posture. About 35,000 people die in sleep each year worldwide due to a sudden unexpected death in epilepsy. It can happen to any epilepsy patient, and it sadly happened to Disney star Cameron last year. Roughly three-quarters of those deaths are related to prone positions, possibly because it is more likely to cause suffocation. And because of this, prone sleep is also an important risk factor for sudden infant death syndrome as well. Sleep postures also indicate Parkinson's progression. Parkinson patients has problem turning in their bed, and more the disease progresses, the harder it is for them to change postures. Some sleep postures, particularly the supine position, can also worsen sleep apnea. Thus, doctors are interested in monitoring sleep posture because this will allow them to manage patients better. So the question is that how can we allow doctors to monitor sleep postures? Many researchers have proposed solutions for this task. Unfortunately, however, existing solutions have some major drawbacks. The first type of solutions use infrared camera to monitor the user when they are sleeping. Yet, as you can imagine, such methods are highly privacy intrusive. An alternative type of solution puts sensors, either on body or under the bedsheet. Those methods address the privacy issue. However, they make sleep uncomfortable, as they require the user to wear sensors or change the feeling of the bed. How can we detect posture without invading privacy or affecting sleep comfort? The solution is to use wireless signals. We don't need any cameras or any other sensors. Our device, BodyCompass, just like a Wi-Fi box. We put it on the wall and it will automatically detect the sleep posture of the user by analyzing the wireless signals in the environment. So how does it work? It turns out that our sleep posture affects the wireless reflection. Let me explain it with this example. There is a person sleeping on the bed with our device on the wall. Our device emits low-power wireless signals and will be reflected back by the human body and the environment. Since the chest area is much larger than the side, and the person is sleeping upwards, the majority of the reflected power comes from the ceiling. And if the user is sleeping facing right, since now the chest is facing to the device, the power of the direct reflection will be much larger, as shown on the right. This gives us the clue to infer the sleep posture from wireless reflections. However, there is a challenge. Wireless signals will be reflected by all the objects in the scene. For example, we have a fan in the room, and it will reflect wireless signals as well. When those reflections got combined together, things will be messy, and it's nearly impossible to infer the posture. So what can we do? Our idea comes from the communication system. When we have multiple sources of signals, we separate them by giving each of them a different modulation. And in our scenario, we do have a modulation naturally. The person breathes while the fan does not. Therefore, only the signal reflected by the person will be modulated by his breathing signals. And this enables us to filter out all the environmental reflections. With those insights, we build our system as follows. First, we collect reflected signals from the environment. Then, we separate them based on which signal is modulated by the user's breathing signal. Next, we feed those filtered signals into a deep neural network, and finally, the model will predict the body angle. The body angle is defined as following: 0 as supine, 90 to the right, 180 for prone, and minus 90 for left. Finally, let's talk about evaluations. We install our device into each of our subjects' own bedrooms, just like the picture shown on the right. In total, we have 26 subjects in 26 different homes, and we have collected 224 nights to evaluate the performance of our system. And let me show the accuracy for each of our subjects. Each bar represents the accuracy for that particular subject, and we can see that our system achieves a good accuracy across all the subjects. And on average, our system's accuracy is 87%. Next, I want to show our system's ability to track the frequency of poster shifts, which is moving from one poster to another. This could be used for tracking Parkinson's disease progression, as we mentioned earlier. We plot the frequency of poster shifts for all 26 subjects, ordered in ascending order. As you can see from the figure, BodyCompass is capable of tracking the frequency of poster shifts accurately, with a relative error of only 10%. In conclusion, in this talk, we present BodyCompass, the first wireless-based system that provides accurate sleep posture monitoring in the wild. Thanks for listening.